Welcome back to the Math Professors. Our YouTube channel covers topics that can be found in any college math class. I'm Professor Van Hamlin, and today I'm going to cover inverse Laplace transforms and transforms and derivatives. So if you liked free content, please consider liking, subscribing, and sharing. So let's get into it. So a Laplace transform takes a function of t and turns it into a function of s. So therefore, that Laplace inverse transform is going to take that function of s and turn it back into a function of t. And we've done this by hand this way. So let's kind of look at some of the Laplace transforms that we've done, or at least types of. So Laplace transform of 1 is going to be 1 over s. Laplace transform of t is 1 over s squared. Of e to the minus 3t is going to be 1 over s to the minus 3, minus 3, which is s plus 3. And then the Laplace transform of the cosine of 7t is s over s squared plus 49. So the Laplace transform just takes these functions and puts them back. So you can see the Laplace transform of 1 over s is going to be 1, or the inverse of 1 over s is going to be equal to 1, and so on and so on. So what I'm going to do is I'm going to write a table of some Laplace inverse transforms that we can practice doing, and eventually how this is going to relate to differential equations. So here are some Laplace inverse transposes. Transformations. So here are some inverse Laplace transformations, and what I mean by some is as you move through differential equations, you are going to build a much larger list than this. So let's just start out with a small list, find some inverse transformations of particular s functions. So what I want to do is I want to find the Laplace inverse transformation of 1 over s to the fourth, and in order to do that, I need to basically figure out, what one of these does it look like the most. So we can see that it has this form like number 2, because I have an s to a power on the bottom, and only that monomial s to a power on the bottom. But if this is a fourth power, that means n has to be equal to 3. So what I actually would like this to say is 3 factorial all over s to the fourth. Now, Laplace transforms are linear, and what that means is if I have the Laplace inverse of some alpha times f of s plus some beta times g of s, then I can pull out constants and then take it over sums and even differences. So this is going to be alpha times the Laplace inverse of f of s plus beta times the Laplace inverse of g of s. So again, it says I can pull out constants, so constants can move in and out of here. So what I'm going to do is I'm going to multiply top and bottom by 3 factorial, and this is going to be the Laplace inverse of 1 over s to the fourth. Now again, I can put constants in and out of this thing, so what I need is I need a 3 factorial over here. So I'm going to put the numerator 3 factorial up at the top. So this is going to be equal to 1 over 3 factorial times the Laplace inverse of 3 factorial all over s, and just to make sure you see that 4 actually is a 3 plus 1, so it does have this form where n is equal to 3, so that means this is equal to t cubed. Now don't forget this 1 over 3 factorial, which is going to be 1/6, so this is 1/6, and this piece right here is going to be t cubed. Alright, so the Laplace inverse of this thing. Now again, looking down here, once you get familiar with these things, you'll know that these will be t to a power, and these will be trig functions. So it looks like this one right here, because I have an s squared plus some it's a binomial with I have an s squared in the bottom, and what I need is if this says 5, I really need to know what needs to be up here. So for it to match this, I need an s squared plus k squared. So let's write that first. So Laplace inverse of 1 all over s squared plus, something squared. And in order to make, this term equal to this 5, I need this to be root 5. Which means I'm going to also need to have, this constant of k down here and up here. So this needs to be at squared, this needs to be just root 5. So I'm going to multiply, top and bottom by root 5. And that allows me to put this root 5 up in the numerator. So what we're going to get is 1 over root 5 times the Laplace inverse of root 5 all over s squared plus that, root 5 squared. And we know this takes this form right here, so this is going to be the sine of root 5t, and I still have that 1 over root 5 in the front. All right, so let's do, I'm going to do a couple more. I want to get really familiar with this. All right, so here's the next two examples. I want to find the Laplace inverse of 3s over s squared minus 64. And again, over here, I'm going to look at, what does it look like the most? So what I can see is it has an s in the numerator and it has that, difference of squares in the denominator. So it looks, like this. So this is going to be the hyperbolic cosine of kt, or the cosh. Now, I don't want that 3 up there. I just need it to be an s. So we know that since, this thing's linear, I can pull out that constant. This is going to be 3 times the Laplace inverse of s all over s squared plus, minus. Now 64 is 8 squared. So we know that it's of this form where k is 8. So this is going to be the cosh of 8t, or 3 times that. Now, for this one, what we know, again, is it's linear, so I can actually break apart the summation. So it's going to be 5s over the denominator plus 3 over the denominator. So this is going to be equal to the Laplace inverse of, I guess I can do all the work. So this is, 5s over s squared plus 16 plus 3 over s squared plus 16. So I know I can break apart this sum to be the Laplace inverse of 3 all over s squared plus 16 plus the Laplace inverse of, 5s. And then this is the 3 over s squared plus 16. Then we have to see, what ones these things look like. Well, these look like trig functions. I have sum of squares in the bottom. The s's are going to be your cosine functions, and the ones that just have constants are going to be your sine function. So this one's pretty straightforward. I can pull out that 5, and I'm going to have now the Laplace inverse of, this is going to be s all over s squared plus 4 squared. So, that already takes this form right here. But for this one, I need there to be, if this is a constant up here, it looks like this one. So I need there to be a 4 in the numerator because this is 4 squared. So what I'm going to do here is I can pull out that 3. And then I can multiply, this by 4 over 4 times the Laplace inverse of 1 all over s squared plus 16. 1 because I pulled the 3 out. And then I can multiply this by 4 over 4. Now, also remember, it allows me to put constants inside and out. So I can take this multiplication of 4 and put it up here. So s squared plus 16 is going to be the same thing as s squared plus 4 squared. So now we have, everything. This is going to be 5 times the cosine of, this constant 4t, plus 3/4 times this is going to be the sine of 4t. Now the last one I want to do as far as Laplace transformation is one that requires a system of equations. All right, so here's the last example. I want to find the Laplace inverse of this thing. Now, if you remember in like a Calc 2 class, we've asked you to take like integrals of something of this form, and this is of that partial fraction form. So we're going to use the same technique to simplify this, so I can use this process of linearity down here. So let's start out with this s squared plus 3s plus 5 all over these factors. And we know this is going to be equal to some a over the first linear factor plus some b over the second linear factor plus some c over the third linear factor. Now I've come up with the idea, like there's multiple ways to do this. I'll show you both ways. I'm not going to do all the algebra immediately. I'll write it out. I'll pause it, write it out, and you can see it real fast. But the one quick way is to use what's considered, I think, the Heaviside methods, or the cover-up method. That if I want to find a, what you can do is you can cover up this s minus 1, and then you can plug in a is equal to 1 into this expression here, and it'll give you the value of a. Now the same thing with b. Plug in -2 here, cover up that factor, and then plug -2 into everything else. And then the same thing with c. Or if these things aren't linear and that method fails, you're going to have to multiply everything by the common denominator. So multiplying everything by these 3 factors, I'm going to have s squared plus 3s plus 5. So multiplying this by both sides, the s minus 1 will cancel. So this would be a times s plus 2 times s minus 3 plus b times the s plus 2's will cancel, s minus 1 times s minus 3, plus c, s minus 3's are going to cancel, so this will be c times s minus 1 times s plus 2. Now, I know I can expand this as much as I can, so this is going to be a times, we have s squared minus s minus 6 plus b times s squared minus 4s plus 3 plus c times s squared plus s minus 2. And our goal really is to figure out our coefficients of s squareds, our coefficients of s's. So I know that I'm going to have, an s squared here, and what I can see is that this is going to be an as squared plus bs squared plus cs squared, so the coefficient in front of s squared is going to be a plus b plus c. Now for your s's, the coefficient is going to be an a times negative x, so it's going to be a negative a. This is going to be b times negative 4s, so this is a minus 4b, and then finally this is going to be c times s, so this will be plus cs. And then finally your constants is going to be negative 6a, and then plus 3b, and then finally minus 2c. Now if you're unfamiliar with this technique, what we do here now is for these polynomials to be equal, that means their coefficients have to match. That means that the coefficient in front of s squared has to be equal to a plus b plus c. So a plus b plus c has to be equal to 1. Now similarly, your 3 has to match this coefficient, so that means minus a minus 4b plus c is going to be equal to 3. And then finally, your 5 is going to have to match this one, so your negative 6a plus 3b minus 2c is going to be equal to 5. Now again, there's lots of ways to do this. You can use techniques in linear algebra, pop into a matrix, row reduce, or we could just do substitution. So I'll pause it, I'll do the substitution, show you the solutions, and then we'll move on to find the Laplace inverse of this. Okay, here's the work that I did for a system of equations. So I solved this for a, plugged it in here, also plugged it in here. When you simplify this, you're just going to get an equation of b and c, and same thing here. Now that I got both equations of b and c, I can see that the 9b and the minus 3b, I could just multiply this by 3, and then I could have opposite signs here. Adding these things allows me to get c, back substituting allows me to get b, and then back substituting again allows me to get a. So now we have the values of a, b, and c. Let's put these things in, and finally find the Laplace inverse. All right, so plugging them in, there's A, there's B, there's C. So now I have the Laplace inverse of, that expression here. So what we get to do is with the process of linearity, we can pull out the constants and really kind of distribute the sum is minus 3 over 2 Laplace inverse of 1 over s minus 1 plus 1/5 Laplace inverse of 1 over s plus 2, and then plus 23 over 10, and we have the Laplace inverse of 1 over s minus 3. And we can see that these things look like, these are exponentials. So this is already of the form s minus a. So this is, a is 1, so this is going to be minus 3 halves e of 1 times t plus 1/5. Now this needs to be s minus a minus 2, so if I rewrite this as s minus a negative 2, we can see that a is actually negative 2, so this is e to the minus 2t. And then finally we have plus 23 over 10 times e to the 3t. Now the last thing I want to show you is the Laplace of really derivatives, and then our next video we can use Laplace and Laplace inverses to solve some differential equations. So finally, here's some Laplace transformations of derivatives. So we know that we already know the Laplace of f of t is capital F of s. So what's a Laplace of f prime, f double prime, f triple prime, and then we'll talk about the fourth derivative to make sure you see some pattern here. So the derivative of f prime is s times capital F of s minus little f of 0. The derivative of the second derivative is going to be s squared capital F of s, and then s f naught f prime of naught, so little f's. And then you can see that f triple prime of t is s cubed times capital F of s minus s squared times f of 0 minus s times f prime of 0 minus f double prime of 0. And what we can see is that the fourth derivative, I'll just do it with parentheses. So let's say f to the fourth of t. What we can see is that we're going to start out with, an s to the fourth times f of capital F of s. Now what's going to happen is that your powers of s are going to decrease, and then your function, little function of f is going to start at the original function, and it's going to increase its primes. So the next one is going to be minus s cubed times f of 0. So now the power is going to drop and the prime on this little f is going to increase. So then this is minus s squared times f prime naught. Again, the power is going to drop and the prime is going to increase. So s times f double prime of 0. And finally, when you get s is 0, that'll be 1, but the power is still, the derivative is still going to increase. So minus f triple prime of 0. And then so on. So again, in the next video, we will use this stuff to solve some differential equations. So if you like the free content, please consider liking, subscribing, and sharing. Thank you.